Okay guys, welcome to the second part of Chapter 10. You should have your guided notes for sections 6 through 9 with you. Open up your textbooks to the beginning of Chapter 10, Section 6, which starts on page 410. Have a calculator ready? Here we go. So we're going to start on Section 6, which is about the gas mixtures and partial pressures. So I'm sure you guys remember this particular gas law from honors chemistry. This is the law of partial pressures, which basically says that the total pressure of the system is the sum of the partial pressures inside of there. So this is the Graham's law of partial pressure. Says that the total pressure of the system is equal to the sum of the molar partial pressures of each gas. So the mole ratios are what give you the partial pressures inside of there. So let me just explain real quick. Here's your example. If you have 2 moles of nitrogen, 3 moles of oxygen, and 1 mole of hydrogen, and the total pressure of the system is 10 atmospheres, what is the partial pressure of just nitrogen? So for this particular guy, we are going to say that the partial pressure of nitrogen, if you look above, is 2 moles. The total number of moles in the system, if you add this all up, 2 plus 3 is 5, plus another one is 6. There are 6 moles total, and then you need to multiply that by 10. So basically you're going to do 2 divided by 6 times 10 atmospheres. I think some of you guys can do this in your head. 2 divided by 6, and then times it by 10. You should get a partial pressure of 3 point, if you want to worry about like sig figs, is basically 3 atmospheres. Alright, so there is one example of the partial pressures, but now watch this. If you're given mass of all of the different gases inside of the container, you still need to convert those masses into moles, because it's all about the mole ratio. So in this particular example, it says now you've got 2 grams of oxygen, 8 grams of nitrogen, and 5 grams of hydrogen. We're assuming ideal conditions here, okay? So I just want to make sure that's clear. It says the total pressure of the system is 10 atmospheres. What is the partial pressure of hydrogen? So what we need to know is the number of moles of each of these. So you're going to have to do a lot of conversions. 2 grams of O2, convert that. 8 grams of N2, convert that, and then 5 grams of H2, convert that. Now I'm going to use some of the simpler masses instead of like the crazy molar masses that I told you with the 4 sig figs. I'm going to try to make this a little bit easier on myself because these are really simple numbers. I'm just giving you a general idea of how to do this. Oxygen is 16 times 2, so this mass is 32 grams per 1 mole. This guy is 14, so double that, that'd be 28 grams per 1 mole. And then hydrogen would be 2 grams per 1 mole. So now we need to just do some simple math. 2 divided by 32. This guy is 0.0625. This guy is 0.2857. And this one is 2.5. Add up the total number of moles, so I'm going to take that 2.5. I'm going to use 2 sig figs for all of these. So 2.5 plus 0.063 plus 0.29. I get a total number of moles of the system to be, and I'm going to use 2 sig figs, 2.9 moles. So the question was, what is the partial pressure of hydrogen? Here's your total number of moles. Here's the number of moles of hydrogen, which is 2.5. So pretty simple. We're going to take that 2.5 moles of hydrogen, divide it by the total number of moles there, 2.9 moles, and then the total pressure of the system is 10 atmospheres. So take 2.5 divided by 2.9 times 10, and you'll get, hold on, I want to check my math, yeah. You'll get, I'm going to use 2 sig figs, so 8.6 ATM. So that's how that works. Always use mole ratios, not mass ratios, mole ratios. Alright, so there's a formula on page 410. So if you go to page 410, there's a formula 10.13. I don't want you to get confused about where this came from. It all stems from the ideal gas law. So if you look at the ideal gas law, you always have to multiply, hold on, You always have to multiply that by this N, that's number of moles. So if you look at the total equation here, pressure total is equal to the addition of all the mole ratios times RT over V. So if I rearrange the ideal gas law to solve for just P, this would be P is equal to nRT over V. So don't get confused about this. It's just the ideal gas law, and you're adding up all of the moles to get to the total molar ratio of the system. So that was pretty easy. I just wanted to show you that one. All right, mole fractions from partial pressures. Mole fractions can actually give you really important information in a problem. You'd be surprised whenever you are doing these problems just how important sometimes those mole fractions can be and how much information you can get out of it. So I wanted you to look at the equation 10.14 on page 411. It looks like this, and I didn't want to spend time to write it on the PowerPoint, so check this out. It says P1 over P total, so this is the partial pressure of one of the gases, this is the pressure total, is equal to N1 RT over V. This is all over the N total, okay, that's what that T stands for, RT over V. This will give you a mole ratio because the RT over V cancels, and so you simply just have the mole ratio of the first, or partial pressure, you know how this was partial pressure, this is like the mole, the part of the mole, over the total number of moles. Alright, so when would this ever be helpful? Well, mole fractions can be calculated by partial pressures, and partial pressures can be calculated from mole fractions. Let me show you. The mole fraction of nitrogen in air is about 0.78%. Now, I want to be specific here. It is 0.78% by mole fraction. Like the molar fraction is 78%. It says, what is the partial pressure of nitrogen at sea level? So here's your partial pressure, 0.78. That's actually your mole fraction right there. See how it says mole fraction is 0.78. So you can use mole fractions kind of like percents. So you can take 0.78 and times it by the pressure of that 1 atmosphere, and you'll get 590 torr, or 0.78 atm. It's pretty easy. So mole fractions, very easy, but you'd be surprised when this little equation can come back and help you when you're in trouble. So we'll talk about that later. Here's another example. The total pressure of the atmosphere on Titan, Saturn's moon, is 1,220 torr. The atmosphere is 82 mole percent nitrogen, 12 mole percent argon, and 6 mole percent CH4. Calculate the partial pressures of each of these gases in Titan's atmosphere. Now I'm going to just give you one of the percents, or one of the partial pressures. And then on your practice problems, on your guided notes, I'm going to make you just do the rest of them by yourself because this is pretty easy. So I'm going to do the partial pressure for the nitrogen. Okay, all you have to do is take 0.82 because that is the molar percent. They make it so easy, and then you times it by 1,220 torr. So I'm going to do this on my calculator. Again, this is the partial pressure of nitrogen. So here we go, 0.82 times 1,220. That's going to give you 1,000.4. So I'm worried about my sig figs. This percent is a whole, perfect percent. You can't, of course, I don't know if that's perfect or not, but usually percents are considered to have an infinite number of significant figures. So you can report it as just 1,000 and not 1,004. This would be the same as like 1.000 times 10 to the third, and that would be torr. So there you go. Alrighty, I'll let you guys do the rest of them on your own. Pretty easy stuff. Alright, do you guys remember how in last class I said that there's something special to be said about when you collect a gas over water? So take this for example. What if I stick some zinc in hydrochloric acid, and then I collect the bubbles in a test tube that has been filled with water? So in other words, I'm doing this reaction inside the solution, and I'm allowing the bubbles to be collected inside of a test tube. I've shown you this before in General Chem. Maybe I should do a demonstration. I don't know if I've got the correct concentration of hydrochloric acid readily available, but this would be a great demonstration for you. So when you do that, when you're collecting a gas over water, you have to worry about the partial pressure of the water particles, because the water particles reduce the total pressure of the system. And so you have to kind of remember that anytime you're collecting a gas over water, you need this formula. Okay, and when does this come in handy? Well, of course I have an example. So let's check this out. And remember, P total is equal to the pressure of the gas plus the partial pressure of the water. So if you're, well, let me just show you. Here's an example. This is a real AP question that I pulled out, and it says the system below is at equilibrium. Okay, so it's totally at equilibrium. And the temperature here is at 28 degrees Celsius. And then it says at this temperature, the vapor pressure of the water is 28 millimeters of mercury. So, all right, think of this container. Yes, this reaction released oxygen gas, but inside of this oxygen gas, why is it not writing? Hello? Okay, hold on. Inside of this oxygen gas is some water vapor. Okay, the water vaporizes and it kind of blocks out the pressure of the oxygen. So yes, there is oxygen gas in there, but there's also water vapor in there. And both of these gases are exerting a pressure on this manometer, pushing the mercury down. Now, since this is a closed manometer, in other words, that means that this area right here is a vacuum. Vacuums do not exert any pressure. So we don't have to worry about whether we should be adding or subtracting from the atmospheric pressure. There is no pressure to compare it to. So this right here is the pressure that this container is pushing on it. So in other words, hold on, P total is equal to 161 millimeters of mercury. But you need to remember what I showed you on the previous screen. Your water vapor is taken away from this total pressure. So 61 millimeters of mercury may be the total pressure, but you need to get rid of the water vapor. So you're going to subtract 28 millimeters of mercury. And when you do that, you will see that the answer is 133 millimeters of mercury, C. And if you're curious, the number of people who got that question right when it was given on the test was pretty low. And this is an easy question. Are you ready for this? Only 45% of the people given this question got it right. Shocking, isn't it? All right, let's keep going. 10.7, kinetic molecular theory. What is the formula for kinetic energy? Do you remember it? It was given, I think, in like the very first lecture that we did. Kinetic energy is equal to 1/2 mv squared. It says, which molecule would have more kinetic energy at the same temperature? CH4 or N2? Guys, this is a trick question because temperature is a measurement of kinetic energy of the molecule. Don't forget that. Guys, the correct answer is that they're the same. Next question. Which molecule would have more kinetic energy? CH4 at 50 degrees Kelvin or N2 at 60 degrees Kelvin? All right, so now we're kind of getting into a more complex type of question, because I'm sure you understand that, yes, mass does have something to do with it. So this particle versus this particle's mass, you have to take into consideration. Their velocity, right, is dependent upon their temperature. But what about their mass? Because that's also part of the equation too. So, oh my gosh, my arrows are awesome. I look like a football star. You know how they like give you the play-by-play action on TV? Anyway, now we're getting into the meat and potatoes of this whole kinetic molecular theory. So hold on to your horses on that question because it's not an easy question to answer. Here we go. So first, we need to give you the basics of the kinetic molecular theory, some assumptions that they make. This is available on page 414. It says the kinetic molecular theory makes 5 basic assumptions, and they're listed on page 414. First of all, they have to move in random continuous motion. Volume of the molecules, okay, inside of a gas are so much smaller than the space between them that the volume of the molecules is considered to be negligible or so small that it doesn't count. The gas particles don't attract or repel one another, and as long as temperature is held constant, the overall energy of the system does not change. In other words, we're talking about perfect collisions where momentum is conserved. And then finally, temperature of the system is proportional to the kinetic or average kinetic energy of the particles. This is the huge one right here. And then we'll talk about when particles actually do attract one another, which gets kind of creepy. We'll talk about that. Here we go. Distribution of particle speeds, average kinetic energy. Even though you read the thermometer of a gas as being 150 Kelvin, there are some particles in that container that are a little bit hotter or faster, and some that are a little bit cooler or slower. Go to page 415. There's a graph up there, and then there's a section, and look at that bolded word towards the top of that page. It says root mean square. It's abbreviated with RMS. All right, guys, don't get your panties in a bunch. But what they want to show you is that in that graph up there, the symbol for root mean square are these little U's, these little funky U's right here. The average speed of all of the particles in there is this root mean squared. Now, on the bottom of page 415, there is a cool little formula for the root mean square. I want you to just kind of check on that, and I will give you more details on this when we come back to class next time, because here's what it says. It says distribution of molecular speeds for nitrogen at 0 degrees Celsius in blue and 100 degrees Celsius in red. Increasing temperature increases both the most probable speed, which is the curve maximum. So guys, the most probable speed, hold on, is right here and right here. Those are the most probable speed. And then there's this other thing called root mean square. The root mean square is, if you look at your textbook definition of what root mean square is, it is the speed of a molecule possessing average kinetic energy. So the speed, again, one more time, this quantity is the speed of a molecule possessing average kinetic energy. And do you notice how they always shift a little bit? So here is the number of particles with that speed down here. Check it out. And then it always shifts over to the right. So here's this one, and it shifts over to the right. I'm going to have to show you this in class because showing it on a PowerPoint is just not going to happen. I don't think I'll be able to explain it very well. All right, so let's just move on for now. Okay, diffusion versus effusion. I'm sure you guys kind of remember this. Here is a great, like, visual, cool representation because check this out. Each of these gases are at 25 degrees Celsius. This is a great reminder that depending on the gas, the mass of the gas, your root mean square shifts an awful lot. In other words, the number of particles with the average kinetic energy, it gets broader and broader and broader. And this is the whole idea behind root mean square, okay? And I'll have to show you next class. So look at this. Hydrogen is the lightest gas. Look at his distribution right here. This is molecular speed, okay? And this is the fraction of the moles that contain that particular speed. So it's fascinating to me that as the gas gets lighter, the average speed of the particles gets broader and broader and broader. Very fascinating reminder. It's just a reminder of how root mean square actually works. So I want you to check out this next formula. This formula is found on page 417. It says the mass, m, of the particles in the lighter gas is smaller than in the heavier gas. It says the particles of the lighter gas must have a higher root mean square speed than the heavier ones. And so here's that root mean square. That's a symbol for root mean square. And then you have all in a square root. That's why I have this to the half power, negative half power. All of this stuff is in a square root bracket. 3RT over, do you remember what that special M means? Guys, that's molar mass, okay? That's that cursive-y looking M, all right? Molar mass. So root mean square, this is how they get it, and I'll show you how to get that next class. Let's go to the next part, Graham's law of effusion. This is a simple one. We've talked about this before in honors chemistry. So how do you use it? Here's how you do it. Compare helium and neon and their mixtures. So here's how the formula works. If you wanted to figure out which one was faster, you'd want the larger number on the top and the smaller number on the bottom, because that'll tell you which one's faster. So nitrogen has a larger mass than helium. So I know already that helium is going to be faster than nitrogen. Helium has a lesser mass than nitrogen, so he's going to be able to move a lot faster. It's the same concept as whether or not, you know, a heavy person can run as fast as a lightweight person. So a lightweight person should be able to move quicker than a heavier person. The same thing would go for like automobiles. If you have, think of it this way, if you have a huge truck moving at 5 miles per hour versus a tiny little car moving at 5 miles per hour, who has more energy? The heavier truck would. So now think of it this way. Which vehicle would have more energy? Like, how can you make those two vehicles have the same energy is the question I'm getting at. How can you make the truck and the car have the same amount of energy? The truck would have to move slower than the car. So for this guy, I want you to realize what we're talking about. We're kind of talking about the kinetic molecular theory, and what you need to realize is that this Graham's law is assuming that they are at the same temperature. Because as long as we keep temperature constant, we can start talking about how they move compared to one another. So if they're at the same temperature, and all we're going to do is just compare their masses, because their masses will give us a better distribution of how fast they're moving at the same temperature. Do you guys remember that picture I showed you? Hold on. I like this picture. Back to this guy. All of these gases are at 25 degrees Celsius. Which gas is moving the fastest? Hydrogen. Which one's moving the slowest? Oxygen. All right. That is due to the fact that these guys, it takes a lot more energy for this guy to move at the same speed as hydrogen. It's going to take more temperature for oxygen to match up with hydrogen. That's the only way that this guy is going to speed up, is if you input more like kinetic energy, which is temperature. So come back over here. So helium is going to be faster, and if I know that, I just need to make sure that I put the larger number on top, smaller number on the bottom, and just keep it straight in my head. I know helium's going to be faster, so therefore you get the number 2.7 when you do your math correctly, and you can say that helium effuses almost 3 times faster than nitrogen at the same temperature. That's the overall Graham's law there, okay? All right, now don't get too panicky on me, but what if I told you that all of the gas laws, like the ideal gas law, the combined gas law, what if I told you that they were all technically wrong to a certain degree? The gas laws assume that gases behave in an ideal way, obeying all the assumptions of the kinetic molecular theory, but guess what? They don't. Guys, gases need to be attracted towards one another. Otherwise, how are gases ever going to turn into a liquid? When gases are attracted to one another, that means that they're allowed at some point, you know, when you drop the temperature, at some point they're going to have to get closer together. When you drop temperature, they condense, right? there has to be some amount of attraction so that they can actually turn themselves into a liquid. It says, then, what is an ideal gas, and under what conditions do the gas laws apply? That's kind of important. It says, in order for the ideal gas law to work, gas particles would have to have no volume, which we talked about, and they could never be attracted towards one another. Now, you know that particles have mass and they take up space because they're called matter. Gas is matter. It has mass and takes up space. Okay. Real gases can be liquefied and solidified when cooled or pressurized, right? Well, when they're pressurized, you can technically pressurize a gas into a liquid or even a solid. Well, you know, that would be CO2, like carbon dioxide. You can pressurize it into liquid. You can pressurize it into a solid. It says ideal gases cannot attract each other to be liquefied. Gases and vapors could not be liquefied if there was no attraction between the molecules, which is interesting. So now we need to talk about how volume and the attraction actually can affect the ideal gas laws. Check this out. So looking at this graph, an ideal gas, check this out, an ideal gas should maintain, you see how PV over RT, what's PV over RT equal to? Think of your ideal gas law, okay? Hold on. PV equals nRT. So what is PV over RT? So they're taking this and putting it on the bottom right here. That's N. An ideal gas, okay, any gas, 1 mole of gas at STP is supposed to be like 1 mole. 1 mole of gas is, right, I'm getting myself confused. 1 mole of gas is equal to, oh yeah, okay, so anyway, if you have a gas at STP, it'll be equal to 1 mole, sorry. Getting myself confused. 1 mole of any gas is equal to 22.4 liters. You guys kind of remember that one? And this is assuming at STP. Alright, so anyway, sorry. I was getting myself a little confused. I was trying to do this and remember this at the same time. So, 1 mole is equal to PV over RT. That's kind of what we're trying to hit at. This is where ideal gases should stay. And this, check it out, this is their pressure. So as we increase pressure, we're supposed to keep 1 mole. But as you can see, that doesn't necessarily happen. Check out some of these gases. This is really crazy. So when you pressurize CO2, this is the most extreme right here, CO2, it dips way down as you increase the pressure, and then all of a sudden, whoop, comes right back up. And then if you check out here, this is CH4. Dips way down and then comes way up high. And then here, look at this. This is hilarious. Here's H2. He's like, doo-doo-doo-doo-doo. Doesn't really dip down. He just goes up. So interesting, huh? Non-ideal behavior. Look at this one. Here's temperature. Okay. This is all the same gas. I can't remember what gas this is. It's one of your diagrams. Let me see which gas this is. Here it is. The effective temperature and pressure on the behavior of nitrogen gas. So, okay, so this is nitrogen. Nitrogen is fairly inert. You would expect nitrogen to be very stable because it's non-reactive. And heck, I mean, nitrogen is what we have in our atmosphere, right? So again, you've got this PV over RT comparison over here. So this is the effective temperature and pressure on the ideal behavior. So check this out. This is where it's supposed to be. It's supposed to be at 1 right here. And that ratio starts flipping out when you increase the temperature. So here is your 200 degree Kelvin. Here is your 500 degree Kelvin, and here is your 1000 degree Kelvin. Hey guys, which temperature gives you the most ideal behavior, like the closest to ideal behavior? If you notice, it's this. Aren't we supposed to keep it at STP, standard temperature and pressure? Isn't temperature supposed to be like, 0 degrees Celsius? Yeah. Look at this comparison here. 0 degrees Celsius, I think, would be the extreme. Let's see, what is this? Would be plus 273.15. That'd be closest to this right here. That's nitrogen at STP. That's the closest that nitrogen gets to STP. Fascinating, huh? Non-ideal behavior. So, how can we get a more accurate value for pressure, volume, and temperature and all that stuff for these gases? How do we get them? How do we get an equation to account for all of this madness? This is van der Waals equation. Okay, it's pronounced van der Waals. The Waals. I know it's, I don't know, German thing. All right, so what you have is you have pressure, and it could be in any of the 3 units, so be careful, but we usually like to keep this in pascals or kilopascals. V is in liters. N is number of moles squared. A. Okay. A, and over here if you look, B, A and B are called van der Waals constants. And these are experimental values that usually have to be figured out through some awesome labs. So if you look at the top of page 423, there's a table 10.3, that gives you a list of all of these values for various gases. So guys, you don't need to panic. They will give you these values on your AP exam, and they will have you just conceptually conceive why the real number, is higher or lower than the ideal number. All right, so this is where it gets kind of complicated, and you have to learn a little bit more about something called periodicity. That would be the periodic trends on the periodic table, and we start getting into things like attractive forces between the electrons. Oh yeah, it gets really interesting. It says, this accommodates for this particular formula, van der Waals equation, will accommodate the attractive forces experienced between gases in a mixture. So if you ever are asked, what is the reason why you got a different value for van der Waals than you did for the ideal gas law, your answer every single time will be that the particles themselves attract one another. The gas particles are attracting one another. Remember, gas particles have to attract one another in order to go into the liquid phase when they're pressurized or when they're cooled down. So, period, end of story. Van der Waals equation accounts for the attractive forces. That's it. Now, there's a sample exercise, 10.16, that begins on page 423, right after Van der Waals equation. In your guided notes, I want you to do that problem so that you can experience what it looks like. And having to do all of that, filling in the P's, filling in the N's, filling in the A values based off of the little table, it's good practice, guys. So please give it a shot. Again, the end of this lecture is doing sample exercise 10.16. Guys, that's it. And I hope that this helped out a little bit. I need to still explain that whole root mean square and how that works. So I'll help you out next class with that, okay? Toodles!